Hello everyone, we're going to be presenting to you furnace selection. This presentation was made possible by Mike Gazdaika, Javier Batista, Gil Henkel, and Locke Boy. To form a component in metal injection molding, the following steps need to take place. 1. Selecting and tailoring a powder for the process. 2. Mixing the powder with a suitable binder. 3. Producing homogeneous granular pellets of mixed powder and binder. 4. Forming the part by injection molding in a closed die. 5. Processing the formed part to remove the binder, termed as debinding. 6. Densifying the compact by high temperature sintering. And 7. Post-sintering processing, including heat treatment or further densification. Based on this process is how we go about in selecting the proper furnace. After molding, the binder is removed from the compact by a process termed debinding. There are several options for debinding based on thermal, solvent, and capillary extraction approaches. For metals, thermal debinding is used most frequently, where the compact is heated slowly to 600 degrees centigrade in air to decompose the binder and oxidize the particles. This oxidation process provides some handling strength to the component after the binder is removed. Several defects can arise in the binding process, especially if the heating rate is more than a few kelvins per hour. A multiple component binder helps overcome such problems by leaving one component in the compact to hold the particles in place, while a lower stability component is removed by evaporation. Alternatively, use of capillary weakening and solvent extraction processes decrease the debinding time, but these are less widely applied as yet. These also rely on multiple component binder systems to progressively open the pore structure while holding the particles in place. Solvent extraction is a rapid technique for the first step of debinding. It has the advantage of speed and good compact shape retention. Example solvents include acetone, ethylene dichloride, and carbon tetrachloride. The next step is sintering, which can be incorporated directly in the binding cycle. Sintering provides strong interparticle bonds and removes the void space by densification. The furnaces used to process the compacts are both batch and continuous types with atmospheres of hydrogen, nitrogen, argon, or mixtures of these. In some instances, vacuum is used with the batch furnace. After sintering, the compact has good strength and microstructural homogeneity, with isotropic properties superior to those available with many other processing routes. Sintering furnace is the single most expensive piece of equipment for the metal injection process. Considerations are process yield, cycle times, furnace loading, daily capacities, depreciation, and continuous are highest yield, medium cycle time, fastest loading, highest daily capacity, lowest depreciation per part. Choose continuous as possible, but beware of the drawbacks. You must maintain a high output, low variability must process similar parts, and there is a high upfront cost. If continuous is not possible, use separate furnaces for debind and sinter. Debind furnaces are cheap compared to sintering furnaces. Higher daily yield compared to a single combination furnace. This presentation was made possible by the generous information provided by Dr. German in Chapter 2 of his book. Thank you very much.